Okay, thank you. Thank you very much. I'd like to start by thanking the IAS for inviting me to give these lectures, which is a great honor and a pleasure to be able to speak here. And especially so for me, as the line of work I'm going to talk about started right here nearly exactly 30 years ago when I was a postdoc here. So the general area of these talks is diophantine problems, but somewhat unusually a focus will be on diophantine problems for non-algebraic sets, certain kinds of non-algebraic sets. And then, perhaps surprisingly, there will be applications to classical diophantine problems, in particular around the André-Oort conjecture and related problems. And in fact, since in doing this, there will be a kind of interaction between algebraic and non-algebraic sets, will be led to certain questions in functional transcendence. So those are all the things. That's somehow the very short summary. Okay. So an overarching theme in diophantine geometry is that systems of diophantine equations do not have many solutions unless there's a geometric reason. And this is the philosophy of geometry governs arithmetic, promulgated especially by Serge Lang. And in this context, not many solutions tends to mean finitely many. And somehow the paradigm or prototype statement here is the Model conjecture of 1922, proved by Faltings. Curve of genus 2 has only finitely many, or 2 or more has only finitely many rational points. And the general conjectures of Lang develop this idea very precisely in terms of the geometrically defined special set of a variety, and the conjecture that outside the special set you have only finitely many rational points. And just as an example of this, it's expected that there are no non-trivial solutions to this equation of writing a positive integer as a sum of 2 positive fifth powers. On the other hand, what's known is that the trivial solutions, where w and x is just a permutation of y and z, at least outnumber the non-trivial solutions. So there was a result of Hooley, and it was improved by Browning and Heath-Brown. And this, at least, so counting solutions by height at least gives you some indication that the solutions are somehow find it less hospitable away from the special set. So that's some kind of example of counting. So I now want to turn to start talking about rational points on non-algebraic sets. And let's consider, for example, a non-algebraic function f, but which is real analytic, say, on some neighborhood of the interval 0, 1. And constructions going back to Weierstrass, even for entire functions f, show that you can have such functions that take rational value at every rational point. And you can elaborate this in very many ways. I think Van der Poorten had a result that the function f and each of its derivatives preserves every algebraic number field. So you can make these constructions. On the other hand, you can show, and this will, that the heights of the points have to increase quite a lot, rapidly, and I'll get to a precise statement of this form that comes by the methods of my this paper with Bombieri, that in a height density sense there really are few rational points on such a curve. And this result was later generalized together with Alex Wilkie to higher dimensional sets, certain non-algebraic sets of certain kinds. A general result which I'll also talk about. And then Umberto Zania proposed a strategy to use this counting theorem to give a new proof of the Manin-Mumford conjecture, which of course is Raynaud's theorem. And then it turns out that this sort of approach has quite a wider applicability. And I guess I'm going to talk about all of those things, so that's somehow the long introduction. But first I want to describe the non-algebraic algebraic connection and how that happens. And this connection is via the arithmetic properties of classical special functions. So if you take the exponential function, which I've modified with a 2 pi I, so that it takes rational numbers to roots of unity, and right, so if you study the rational points on this set I've called curly capital Z, you study the rational points on that set, which is generally a highly non-algebraic set, then that gives you a possible route, maybe not a very plausible looking route, to study roots of unity on a plane curve fxy equals 0. So that problem is a famous toy problem of Serge Lang, with proofs by Ihara, Serre, and Tate in connection with Manin-Mumford and Mordell-Lang. And if you replace the exponential function by the modular function, the j function, which takes quadratic points in the upper half plane to so-called singular moduli, which are the j invariants of elliptic curves with complex multiplication. And these numbers, the singular moduli, have a very rich arithmetic structure going back, I mean, it's been studied since the 19th century in connection with complex multiplication of elliptic curves. So now if you study quadratic points, ZW, in the upper half plane, so just points which are in the upper half plane and quadratic over the rationals, for which the j functions satisfy some polynomial, then this is in general some non-algebraic set. And if you study quadratic points on that set, then that's a possible route to studying points on fxy equals 0, which are singular moduli. And that is the very basic case of the André-Oort conjecture, which in this case was proved by Yves André in 1998. Right. So, okay. So in this lecture, I want to describe the counting result and sketch these applications. And I'm going to postpone a little bit describing exactly what kinds of sets we can count points on to the next lecture. We'll see. I'll give a kind of provisional definition, which is somehow, well, not the right definition. And then I want to sketch these diophantine applications. And then later in the third lecture, I want to describe a more recent diophantine conjecture which somehow unifies André-Oort and Mordell-Lang in a much bigger conjectural picture, and a conjecture which was made sort of independently and from different motivations by Boris Zilber, by Bombieri, Massa, and Zanya, and somehow in the most general form by Richard Pink. Okay, so now to start some actual business, I want to define the counting function. So we're now going to take some, for the moment, arbitrary set z in R to the n and a height parameter t, and I'll let zqt. So that's got the little hand is on the middle there. ZQT will denote simply the set of points on Z which are rational. Each coordinate is rational and has height at most t, and this is somehow the very naive height of a rational number is the maximum of numerator and denominator in the lowest terms. And then the counting function nzt will simply be the cardinality of that set of points. And then we'll need this. We want to talk about quadratic points at some point, so I put down this definition. You can extend the height to number fields, to algebraic numbers in the usual way. And then we can count points on a set Z which are of degree D. So we simply demand that each coordinate is an algebraic number of degree at most D, and that the height of each coordinate is at most T. And then we have this set of points and its cardinality, the counting function. Okay, so the basic result, which goes back to the methods of this paper with Bombieri, is about counting the rational points on a non-algebraic real analytic function. So we have f analytic on some neighborhood of 0, 1, and z is the graph just on the interval 0 to 1, and we go counting the rational points. And the conclusion is that given for any epsilon, the number of points is t to the epsilon with some constant. And I'm going to describe the proof of this theorem, which depends on this lemma of Schwarz, a kind of a mean value theorem. So in the lemma, you have capital D functions, each of which has d minus 1 continuous derivatives on some interval, and you have capital D points in the interval. And you let delta be the determinant of the functions, the alternate, evaluate the functions at the points. And the theorem is that this delta is actually equal to the Vandermonde on your points multiplied by some kind of determinant of derivatives at some suitable intermediate points. And the consequence of this is an estimate for this determinant in which you have some constant which comes, so I've somehow rearranged because we tend to put the garbage and the constants out front. So there's some constant that comes from this determinant, the maximum of the derivatives, and there's d factorial terms, and so on. And then, of course, there's simply estimating the Vandermonde in the very crude way. It's just the width of the interval to the power capital D, d minus 1 over 2. Okay, so that's our lemma, and now we're going to apply the lemma. If we can find, right. So here's the proof. And what this proof does is to show that the rational points up to height t that are somehow reasonably close together on the curve must lie on an algebraic curve of some degree that you fix in advance. And it's a kind of typical transcendence style argument, which somehow depends on the one hand on the fundamental theorem of transcendence theory, that there are no integers between 0 and 1, and on a zero estimate. Okay, so here's the proof. So you fix some degree, small d, and capital D is simply the number of monomials on two variables of degree at most small d. And we're going to apply the lemma with the capital D monomial functions x to the I, fx to the j. And all these functions, of course, are rational on the points that we want to consider. And now we suppose, so our whole function is on 0, 1, but we're going to consider we've got some points xk, which all lie in some smaller subinterval j. And we form this determinant. So the xk's and the fxk's all belong to the set of rational points of height up to t, and we form the determinant. And then this determinant delta, and this is the crucial thing, that on the one hand, it's a rational number, and if you look at what it takes to clear the denominator, it's something bounded by t to the little d, big D over 3. If you just, right, because there are d plus 1 monomials of each degree d, and you just add those up. On the other hand, the physical size of delta by the lemma is bounded by some constant depending on f and d and all the derivatives up to order capital D minus 1 times the width of the interval to the capital D, d minus 1 over 2. And the crucial thing is that dd, the growth in the height is roughly d cubed, but the physical size is getting small at the order d to the fourth. And that means that if, well, so this is the calculation written out there, but if the size of that interval raised to the dd minus 1 over 2 is less than t to the dd over 3 with the suitable constants, then the determinant is 0. That's the no integers between 0 and 1. And of course, if you sort of now take the d minus 1th root in all of this and work out the width of the interval, you discover that the interval 0, 1 can be covered by this many intervals. And that number, 3 over d plus 3, can be made to go to 0. So now what you do, of course, if you're given epsilon, you choose d such that 3 divided by d plus 3 is less than epsilon. Now you divide into the subintervals. In each subinterval, all the points lie on one algebraic curve of degree d. And now comes the 0 estimate that for our analytic curve, that's a bounded number. The intersections of the analytic curve with curve of degree d is just some bounded number. And so you multiply those things together and you get your t to the epsilon. Now I want to observe, so that's the end of the proof. I just want to observe at this point that what you require to do this proof is actually somewhat less than that the function be be analytic. You just need somehow these two elements, which it's maybe not clear how you would get them, that you can somehow parameterize it by functions with sort of an arbitrary pre-given number of derivatives, and then you need this 0 estimate property. Okay, so now I want to talk about higher dimensional sets. So we take some z now set in R to the n, and we want to count rational points. And our idea is that if this set z is somehow non-algebraic, then it should have few rational points. And we want some general estimate of this kind. But to have somehow any reasonable hope, we have to impose that this set z should be somehow geometrically reasonable. And the condition that we're going to actually take is that this z be definable in an O-minimal structure. But I'm going to defer discussion of what that means and where it comes from to the next lecture. And for the moment, I simply want to note that if you take a real analytic function on a neighborhood of a bounded box from 0, 1 to the k, say, into R to the n or 0, 1 to the n, then the image of that map is a definable set. So that is a kind of provisional definition. The actual definition is broader and crucially broader for the applications, but that's a provisional definition. And the other feature that we have to deal with when you have a set, a higher dimensional set, is that it might actually have algebraic, positive dimensional algebraic subsets, even though the set itself is not algebraic. So the most obvious example of this is something like z equals x to the y. That's a non-algebraic set. And it will be definable certainly, I mean, if you restrict it, if you stay away from the singularity, it'll even be definable in these terms. But even with the singularity, it'd still be definable. But it has lots of rational curves in it, and they indeed will have quite few rational points on them. So we're going to stay away from that, and we make this definition of the algebraic part of a set z. Z-alg is the union of all connected positive dimensional semi-algebraic subsets of z, so whatever that is. And I'll just remark here that semi-algebraic in Rn means that you're a finite union of sets in Rn, each of which is defined by finitely many algebraic equations and inequations. So that's
But
that.
does that union have some nice, retain some nice structure? Like, is it necessarily semi-algebraic?
Is this union? No, this union might be quite bad.
It could be quite good.
And you see it here. It's a countable union. In fact, this algebraic part is in general not a definable. If Z is definable, Z alg might be not definable and quite bad. But we'll see eventually actually that, so I'm going to now state a theorem where we exclude all of this set. But it turns out that if you eventually look at what you're proving, you don't need to exclude it all. And you can sort of refine the statement. But that's somehow we'll get. So for the moment, I just want to state it like this. So this is my theorem with Alex Wilkie. So you take a set Z, which is definable in an O-minimal structure, and epsilon. And then if you look away from the algebraic subset, you get at most t to the epsilon rational points for every epsilon. So you can view, if you like, I mean, this was part of the idea of it, this algebraic part you can view as being a crude analog of the special set in diophantine geometry. It's the part, these algebraic things inside Z might or might not have lots of rational points on them, depending on what kind of algebraic sets they are. And so you can view this theorem as a kind of a crude analog of Lang's general conjecture. Well, and I've said it here, you can actually do a bit better than excluding the whole Z alg. And maybe I'll just remark here that you can do the same thing for counting points of any degree D. And maybe the last thing also, though this won't come up so much today, is that this result is actually uniform in definable families. So if your set Z is really the fiber of some set Z, in R to the n cross R to the m, where the R to the m are some parameters, and for each t in R to the m you have a fiber zt in R to the n, then you get the same statement in which the constant is independent of the fiber. Okay. So now I want to somehow move to the diophantine applications, and I want to start with with Lang's problem, or with its sort of higher dimensional version, just to give somehow an example, first run through of how this strategy works. So here's Lang's problem that I alluded to early on. You have V in C cross squared, a curve defined by some polynomial fxy equals 0, and you go looking for points on the curve whose coordinates are roots of unity. And the theorem says that there are only finitely many such points unless f is of a very special form, and the form is that that V is essentially a subgroup, or a coset of a subgroup by a torsion point. So in other words, f is of the form x to the n, y to the m equals a root of unity. And of course, you can see in that case that you really do get infinitely many. So it's somehow, it's a sharp statement. Now, when you move to higher dimensions, so V now is subset of C cross to the n, you have a new phenomenon which can happen, which is that your set, your algebraic set V might actually contain positive dimensional subgroups or cosets of subgroups which might contain infinitely many torsion points. So your new statement becomes that your variety V contains only finitely many maximal torsion cosets, and they might be individual torsion points or higher dimensional things defined by multiplicative equations. Right. And you can state it somehow in various ways. that all the torsion points lie in finitely many torsion cosets contained in V, that the union of all torsion cosets contained in V is a finite union, or I somehow like this statement, that there are somehow finitely many maximal things. So I want to sketch the proof of this, which we're going to reformulate, of course, in terms of the exponential function. So here's the exponential function. And later, in order to somehow apply these real variable methods, we're going to identify C with R squared. And I'm going to let this capital F be 0, 1 cross R. So this, if you like, is fundamental domain for the action of Z by translations on C, and then on its nth power. And if we recast it in this way, then if you take your subvariety V in C cross to the n, then what you're really saying, well, if you look at the inverse image of V and you look at the rational points in the pre-image, that what you see there are somehow a finite number of lines up to the Zn action. They correspond to the finitely many, not lines or rational hyperplanes, or their translates. And okay, so I'm going to sketch the proof, and we first observe that in doing this, we can assume that the variety V is defined over the algebraic numbers, because roots of unity are algebraic, so we can assume V defined over a number field. And then I take Z to be this set. I take the inverse image of V under exponentiation, and I intersect it with F to the n. And this set is definable in an O-minimal structure. So we'll see that, although it's not of the form that I described. But this set is definable, and the full pre-image isn't, but somehow everything that happens inside the fundamental domain. After that, it just repeats. And the first step in this are these opposing bounds. So on the one hand, a torsion point in V of order n, if that's the largest order of a root of unity there, it has nearly n conjugates. Somehow, certainly more than n to the 1 minus epsilon. This is a very elementary thing you can find in Hardy and Wright, the number of, Galois orbit of a root of unity. So that if you've got one point like this on V, it gives you a rational point inside this Z, and the rational point has height at most n, because it's a rational number in 0, 1, whose denominator is at most n. On the other hand, it has nearly n, so certainly much more than n to the half conjugates. And now if you apply the counting theorem with some epsilon less than a half, then you'll find that if this set V has even one torsion point of large degree, then this set Z has too many rational points, and there has to be something in the algebraic part. There have to be positive dimensional semi-algebraic sets inside this set Z. So that brings us there. And so now once you've got a positive dimensional semi-algebraic set in Z, you observe that this set Z itself is a complex analytic set. And so you can analytically continue this set A, and you'll actually conclude now that you get a positive dimensional complex algebraic set W inside the exponential pre-image of your set V. And somehow now, instead of thinking about points, this has become a problem about positive dimensional sets and functional transcendence. So when can it happen that, if you like, you can have complex algebraic set W inside the pre-image of an algebraic set V under exponentiation, or if you like, when can the image of W under exponentiation be not Zariski dense? So again, this is something that's answered by, as a very special case of this theorem of Ax. So Ax proved a functional version of Shanwell's conjecture, and I'm going to talk about that much more in the next lecture and its generalizations. But a consequence of that is the following statement, that if you take an algebraic set W in C to the n and you exponentiate it, that this will be Zariski dense in the image unless your set W happened to be contained in a translate of a proper Q subspace. And in that case, you can obviously get exceptions because the image of that set, L, of course, is some kind of a translate of a torus. So you can obviously generate examples of e to the W contained in V in that way. And Axis that that's the only way. And what this means is that if now e to the W, if W is not Zariski dense, it's contained in some L, maybe it now is Zariski dense in e to the L. If it isn't, you can repeat the process. If it is, that means that e to the L is also contained in V by the Zariski density. And so another way of stating this is that a maximal algebraic subset in the pre-image is always a translate of a rational subspace. So these translates of rational subspace I'm going to call weakly special subvarieties for sort of consistent, forwardly consistent notation. And I call this theorem Ax-Lindemann because it's somehow the functional analog of Lindemann or Lindemann-Weierstrass theorem. So Lindemann's theorem would say that if you take algebraic numbers, then their exponentials are algebraically independent unless the numbers, the algebraic numbers, are linearly dependent over Q. And this is somehow the functional statement that e to the W, the exponential of the algebraic set, is Zariski dense unless there's a rational, it's contained in a translate in a weakly special subvariety. Okay, so that's the second step. Now when we find we've got these semi-algebraic things, we know that we find weakly special things. And all of a sudden we see that the algebraic part of our set Z is not a mess. It's actually built up out of rational translates of rational subspaces, and it coincides more or less with the exceptional case in the theorem that we're trying to prove. So the last step we need is a finiteness statement, which is that the weakly special L's that come up, you're given V, the weakly special L's that come up come from finitely many, they're the translates of finitely many subspaces. And there are somehow three ways of proving that. One is a kind of explicit and effective argument that Bombieri, Massa, Zanya give. A second argument, because we're going to see this same format play out and we'll need somehow an analog of the same result. But a second way to do it actually uses O minimality, because what you can see is, in fact, that the set of slopes that occur, the slopes of real subspaces that have translations that appear maximally among such things in the inverse image, that set of slopes is a definable set. On the other hand, we've just proved that everything in it is rational. And we'll see that this somehow forces finiteness, because actually definable sets in O-minimal structures only have finitely many connected components. So you can't have, well, once you know that every point in it is rational, you get finiteness. And you can also view it as simple model theoretic compactness argument. And then somehow there's an inductive scheme that takes over, because once you know you have finitely many families, for each family you ask which translates of that subspace are contained in V, and that leads you to consider the points on some lower dimensional variety. So that after that, it's just an inductive scheme. Okay, so now I want to indicate how somehow the same scheme works for the modular case of André-Oort. So, right, so the André-Oort conjecture is an analog of Manin-Mumford for Shimura varieties. And I won't somehow give the full statement. But the simplest case arises simply by replacing E, the Cartesian product of the exponential function, by the Cartesian product of the j function. So you just replace that j mapping from h to the n to c to the n. H is the complex upper half plane, and here is the q expansion of the j function. It's a holomorphic function in the upper half plane. Right, so I somehow need to explain what the analog of the torsion points and the torsion cosets are in this situation. So let's recall that the j function is connected with the theory of elliptic curves. It somehow parameterizes elliptic curves, well, by the moduli, by the j invariant. So it's a holomorphic function. It's invariant under SL2Z. And it parameterizes elliptic curves. So an elliptic curve is the quotient of C by some lattice. If you take the lattice generated by 1 and tau in the upper half plane, and you get the elliptic curve E tau, then the j invariant of that elliptic curve is j of tau. And so the invariance under SL2Z is a consequence of change of basis of the lattice. And in addition to the SL2Z invariance, if you operate on the variable by matrix with rational coefficients, then those two functions are algebraically dependent via the classical modular polynomial. So there's an example of one on the next slide, I think. So here is the classical fundamental domain for SL2Z acting on the half plane. So this, the gray domain. And for example, if you take x to be j of z and y to be j of 2z, then those two functions are algebraically dependent by the modular polynomial phi 2, which is this polynomial. And they're all symmetric polynomials with integer coefficients. So now we come to the singular moduli. So the singular moduli are the special values of the j function, and I guess I already basically said what they are. They're simply the values of j at quadratic points. Those are the singular moduli. But they correspond to elliptic curves with complex multiplication. So endomorphisms of the elliptic curve correspond to complex numbers mu, which multiply the lattice into itself. And generically, the only mu's which do that are integers. But if tau is quadratic, it's a kind of an elementary thing that you get. There are non-integer mu's which do it, and that's the complex multiplication. So, right, so these are the singular moduli, and they have very rich arithmetic. It's a famous theorem of Schneider that these are the only algebraic points which are also algebraic under the j function. and they're algebraic integers, and here you have some examples. Right. So here then is the theorem of André. So now we take a subvariety of c squared, and we go looking for points on the curve V whose coordinates are singular moduli. And the theorem is that V contains only finitely many such points, special points, unless V is a special subvariety. And the special subvarieties are either a modular curve, phi n of xy equals 0, or a vertical or horizontal line on a singular modulus. And it's again the case that those cases do have infinitely many, right? If you take vertical or horizontal on a singular modulus, you'll obviously run into all the singular moduli on the line. And the modular curve does too, because the two curves, elliptic curves, whose J invariants are related by a modular curve, the two curves will be related by an isogeny, and if one is Cm, the other is Cm. So these curves do have infinitely many. And so this theorem is somehow the analog of Lang's theorem, the Ihara-Serre-Tate theorem, about torsion points on a curve in C cross squared. So André proved this unconditionally. In the same year, Edixhoven proved it under GRH, and then that started a program of proving further cases of André-Oort under GRH, which eventually led to a full proof under GRH. So I want to state the theorem in C to the n. And so I need to tell you what these special points and special subvarieties are. So the special points in C to the n are simply n tuples of singular moduli. So there's a few ways of describing the special subvarieties of C to the n, but so this is one way. So firstly, if you apply a modular relation to two coordinates, you'll get some hypersurface in C to the n, and that's special. And if you set some coordinate to be fixed, to be a singular modulus, that's special. And on the other hand, if you intersect two special things and take irreducible components, then that's special. So that actually describes the special subvarieties in C to the n. Another way, I mean, it's equivalent to saying the following, that the images of maps, so you take Z in the upper half plane, maps to its image under some number of GL2Q matrices, that gives you a curve in C to the k. Well, it gives you a curve in H to the k, sorry. Then you apply the J function, and then you're in C to the k. That curve is special, and you can take Cartesian products of such things and special points. And we're also going to need the notion of weakly special subvarieties in this situation. And that is the same, but we allow hypersurfaces where you fix xk to be anything, not just a special value. Okay, so modular relations or xk equals constant. And then the André-Oort conjecture, the theorem in this case, is that subvariety V of C to the n contains finitely many maximal special subvarieties. So there may be points or higher dimensional things, finitely many. Right. So I want to sketch the proof of this, which is exactly analogous to the previous proof. So special points are algebraic, so we can assume that V is defined over a number field. I guess I made that assumption in the first case, and then I didn't reference where I used it, but we took Galois conjugates. So then we want V to be over some fixed field. So, and we're going to do that again here. So V is defined over a number field. So we've got the J function. and we identify c to the n with, or h to the n with some semi-algebraic subset of r to the 2n, and we take z to be the pre-image of v intersected with the classical fundamental domain to the nth power, and we view that as a subset of r to the 2n, and this is a definable set. And so now, okay, a special point sigma in V has some pre-image in Z, which is a quadratic point, because the special points are the images of quadratic points, and there'll be such a pre-image, of course, in the fundamental domain. The quadratic point, each coordinate, tau, I, this is just a quadratic irrational, and it has some minimal polynomial over Z. It satisfies some minimal quadratic. And that quadratic has a discriminant, which is a convenient complexity measure of this point. And I'll take the d of tau to just be the maximum of the discriminants of each of the coordinates. Right. So the first step is the opposing bounds. So it's a very elementary thing. If you look at the definition of the fundamental domain in terms of the A and the B and the C, you just see immediately that the height of this point tau is bounded by the discriminant. That's a very elementary thing. On the other hand, the theory of CM, complex multiplication, tells you that the degree of sigma of the singular modulus is equal to the class number of the order whose discriminant is with that discriminant. And the size of the discriminant of the class, the size of the class number is bounded below by the size of the discriminant to the half minus epsilon by classical and ineffective theorem of Siegel. So the sigma, the singular moduli, has many conjugates, roughly d to the half, but each one of them gives you a quadratic point on your set Z whose height is bounded by d. So again, as soon as the discriminant is large enough, you apply the counting theorem with some epsilon. Well, if you like, you choose this epsilon to be whatever you like, and then you choose the other epsilon in the counting theorem to be something smaller than a half minus that. And of course, when you take Galois conjugates, a positive proportion of those will again land on V, and you'll get another quadratic point in Z. And so if you have points in V of large discriminant, you're going to end up with that the algebraic part of Z has to be non-trivial. You must have positive dimensional semi-algebraic things inside the set Z. Right. So the second step, again, is functional transcendence. So from the positive dimensional semi-algebraic set, you get, by analytic continuation, you get a positive dimensional complex algebraic set sitting inside the J inverse of V. So this is where I should say, of course, that when I say that J inverse of V contains an algebraic set, positive dimensional algebraic set W, I have to somehow be a bit careful what I mean by this, because there are no algebraic sets that live only in the upper half space. They leave the upper half space, but I guess, so algebraic, so if you like, an algebraic subset of H to the N simply means a connected, sort of complex analytic component of W intersected H to the N for a true algebraic subset of C to the N. And what we find here is that we get some positive dimensional W, complex algebraic W, which is inside the J preimage of V. And the theorem that we need here is the corresponding Ax-Lindemann theorem that in the previous case came from Ax's theorem, Ax-Shanwell, which says that if you get anything positive dimensional algebraic inside J inverse of V, then in fact you get something weakly special. The maximal such W is always weakly special. And another way of saying this is that if you take an algebraic set which intersects the upper half plane to the nth power, and you apply J to it, then what you get is Zariski dense in C to the n, unless W is contained in some proper weakly special, which means that some coordinate is actually constant on W, or two coordinates satisfy a modular relation. Oh well, a fixed G relation where G is in GL2Q. Right, so in particular this implies, which I should have remarked in the exponential case, that the only algebraic varieties whose image is actually algebraic under J are actually the varieties in upper half plane to the n defined by equations of this form, some coordinate constant or some number of constant coordinates and some others related by GL2Q. And there's an interesting thing here that if this JW is not Zariski dense, which means that the J's of the coordinate, the n coordinate functions are algebraically dependent, then in fact two of them must be dependent, or even one of them must be dependent. You can never have a situation where three of them are dependent without one or two of them being dependent, which is quite a peculiar thing. Now, so I want to sketch the proof of this sort of briefly. I'll be talking a lot more about this in the next lecture, because the proof of this theorem actually goes by point counting again. It uses the counting theorem again. So how does this go? Where have I put it? Ah, right. So here's the sketch proof. Okay, so we suppose we've got W contained in J inverse V, and it intersects the fundamental domain. And then by the invariance of the J function, every SL2Z to the n translate of this W is also sitting in the pre-image. And in fact, you can prove that rather many of them also intersect the fundamental domain. So the way, and I'm not sure, I mean, the way to think about this is that you've got, this is the upper, this is f to the n, and here we've got our subset Z, which of course continues, and W is inside there. But now if you continue this W, so this is W, and wherever it goes, if it goes through a fundamental domain here, then the back translate of this is back here and must be inside Z. So what you prove is that as you follow this W, it goes through very many different fundamental domains, and every time it goes through a fundamental domain, there's an SL2Z translate, which takes you back and gives you another copy of it, so to speak, which is inside which meets your set Z. Now, on the other hand, so SL2Z, of course, is not going to be a definable set, but SL2R is. That's just a semi-algebraic set. So we can look at all the SL2R translates of W and ask which ones intersect the fundamental domain and meet Z, are contained locally in Z. That's something that's a definable condition. So we end up with a definable set that has many SL2Z points. Those are integer points. And what this means is that by counting, you must have positive dimensional semi-algebraic set, and that means that you can now try and make W bigger by simply taking the union over this algebraic family. So you try to enlarge W in this way. You've got a positive dimensional family, But if you assumed that W was maximal, then you can't enlarge it, and that must mean that W is stabilized by a lot of elements. And if you play this game, I mean, there's quite a bit of, you have to work a bit from there, and I'll describe a bit more in the next lecture how that work looks. But you eventually prove that this W must be weakly special. And so, right, so so this proof uses counting again, but now it's a sort of a different counting, because in the first part, with the opposing bounds, you're looking inside the fundamental domain and you're counting quadratic points. And somehow here you're looking outward from the fundamental domain and counting fundamental regions that this W goes through. Okay, and then there's a conclusion, and I can see I'm running short. But again, the conclusion is a kind of inductive scheme that you need to know that the set of maximal weakly special subvarieties that you need to deal with are the translates of finitely many, which means the modular relations are all fixed and you can only move the constants. And then there's a kind of inductive scheme, which is sort of reduced to lower dimensional problems. This theorem is ineffective somehow in three ways. I mean, one way would be good enough. Of course, the Siegel lower bound is highly ineffective and depends on Siegel zeros and this somehow very ineffective argument. The counting theorem is ineffective as it stands, although there's quite a lot of progress towards making it effective in various cases and also improving it in various ways. So I just wanted to remark here that the only effective case of André-Oort is the case of C squared. So André's proof was unconditional but ineffective, but Kuna, Bilu, Massa, Zanya have an effective proof.
So what do you mean by effective?
I'm sorry?
Well, what do you mean by effective?
Well, what was the source of ineffectivity in André's proof?
I think it was also Siegel type things. But this uses Baker. Kuna uses Baker linear bounds for linear forms in logarithms. Yeah, well, okay, and they also, Bilu and Kuna, can prove André-Oort effectively for linear subvarieties of C to the n. I'm sorry?
What does effective mean?
It means you can give an actual bound. I mean, it means in principle you can bound the discriminants of the special points that you see. And then, in fact, even made it in some cases fully effective where they proved, for example, that there are just none on. I mean, you can actually carry this out and really prove. It's not like 10 to the 10 to the 30, in some, if you know what I mean. In some cases, you can sort of actually prove there are none. Right. So I wanted to talk briefly about the André-Oort conjecture in general. So again, it's the same statement, and the whole. So this is conjecture of André and Oort, somehow made slightly different cases, and it's the same statement for a Shimura variety X, and this X Shimura variety. I don't want to go into the formal definition, but it's an arithmetic quotient. So you have some Hermitian symmetric domain omega, and you have its quotient by a suitable arithmetic group. The paradigm examples are the Siegel modular varieties, and these things have a collection of special subvarieties which are somehow the Shimura subvarieties in a compatible way. And then you have the same conjecture. So maybe, okay, I'm really running out of time. So maybe I should just say that Ulmo showed, so in principle, this same strategy you can apply to the general case. They all look good, I mean, in the sense that special points always correspond to some algebraic points of bounded degree up in the Hermitian domain. And then Ulmo showed that if you had somehow 4 specific ingredients, then you could carry out the proof. And so there's been various progress on all of these things. You need the appropriate set to be definable. So that was done in various stages. In the most general case, Klingler, Ulmo, Yafayev, and also even Bakker and Zimmermann for period mappings. You can go into more general settings. You need the Ax-Lindemann, which I'll say more about next time, but that's also fully proved. And you need the Galois lower bounds for Galois orbits. So at the present stage, Zimmermann proved those for AG, and that was somehow the last step in proving the André-Oort conjecture for AG. And that's the only missing element to a general proof. So I think I have here the André-Oort conjecture. So you have André's unconditional result, the full result under GRH, sort of the counting results, the general result that's only missing the Galois orbits. Xi and Gao showed that if you had, you could do the mixed cases wherever you could do the pure cases.
And so GRH was basically used to give lower bounds for Galois orbits. There's really a difference between 2 and 4 in some sense?
Yes, there is, because they use the Galois orbits, they use the GRH to get a small split prime, which is something more than just knowing that the orbit is big. So here you just, right, so here you just need a lower bound, whereas those methods needed more. Right, so I'm going to finish right on time, but so in the next lectures I'm going to talk more about what it means to be definable in an O-minimal structure and where that all comes from, and then describe further these functional transcendence properties. And in the third lecture I'll talk about the Zilberpink conjecture and the point counting approach to those problems. Okay, thank you very much.